this up to about maybe 5 or 6 cycles per second.
Why?
And okay, so this is bobbing up and down 6 times per second. Okay, and you can see the front screen. You see some bright areas and you see some not so bright areas. Okay, and the distance from bright area to bright area is what? What do you think? Okay, what is it called? Good.
Wavelength.
That is the wavelength, okay? The bright area that you're seeing is actually the trough of the wave that's produced because a lot of light can get through. The darker areas that you're seeing is actually the crest of the wave, okay? And you can see the distance between those is kind of big. But look what happens if we increase the frequency of this wave. I'm going to double it here for you.
Whoa.
So now what happens?
Wavelength smaller.
Distance from, if you kind of move your eyes and you follow with it, can you see? Okay, you can see up here too, right? The distance got smaller, so what happened to the frequency?
It increased.
Good. And the wavelength?
It increased. It got lower.
Got smaller. Good. Okay, so some of the fun things that we like to be able to do with this are to be able to track it and study it, or also we like to see how does that wave face interfere when it hits other things, okay? So one thing that we can do is we can match the light that we see with the frequency that this is produced. All right, and it'll take me just a second here because this is going to...
I can't do this.
Okay, hold on. We'll crank this up so it's not quite...
That's what I'm gonna do is shaking.
20 works pretty good.
Let's make me blind.
No. Okay, so now,
Do you see that thing floating?
you remember that the waves were going across the tank earlier? They're still doing that, okay? But this is bobbing up and down 20 times per second, and the light is shining at 20 times per second. And so you're catching it at such a rhythm that the light catches the same wave doing the same thing all the time, and it looks like it's not moving at all. Okay? Now we could change the phase of the light. You want to do that? Okay, we could change the phase of the light just a little bit, so it catches it a little sooner or a little later, and look what you see. Now you can see the wave going across the tank. It looks like a constant velocity. It's moving actually quite a bit faster than that. It's just where the light, when the light goes off, that's when we're catching it, okay? One thing that's interesting to watch when we see this, we could change the frequency so that it is not, so that it's on the back side of that. And look what happens.
Wait, how'd you
It
look?
only appears to go back.
It's appearing to go backwards. It's still going forward,
Yeah.
okay? But now you're catching it at a delay. Have you ever seen a helicopter propeller that goes around and all of a sudden it looks like it's going backwards?
Yes, ma'am.
That is the same thing that's going on here, okay? Because of where you're catching it and where it is in its motion, it makes the motion look like it's going backwards. So we'll go back forward again here.
It's one of those things we call an optical illusion.
All right? And so one thing that's interesting to see with this is we can see what happens when our wave strikes a barrier. Okay, so we're sending a wave through the area here, and we're going to take this is a flat barrier, but I'm going to put it at an angle here. Let this settle in here. Okay, you can see the waves that miss the barrier, they keep on going around. Back over here. But the waves that hit this barrier bounce and go that way. So can you see this little cross pattern over here? See where it looks like it's kind of crossed?
Yeah.
So waves that are coming this way are meeting waves that are going that direction, and they are interfering with each other. Okay? And so then we can see that interference pattern as it shows up. This is still vibrating at 20 cycles per second, and so it's hitting that and moving off at 20 cycles per second. We have this set so that you can see it. Right? The other thing that's interesting to see is what happens if the shape of our barrier is a little different. So here I have a curved barrier that we were going to send straight wave pulses into. And if I speed this up a little bit.
I know, I figured it out.
Does that not help? Can you see the central point where those come to? In the ceiling off the curve? Can you see the point that comes to? These waves bounce off, and these are flat waves going into, hitting this curve, and they're coming back to a central point. Do you know what that point is called? Kind of like that. Starts with an F.
Focus point.
The focal point, a focus of a parabola. Okay, the focal point of a parabola. Another interesting thing that can happen
Why?
is we can take a flat barrier and we can send our waves into this barrier, but we can have an opening here. Okay, so we're sending straight waves. We're sending straight waves into the barrier, and what's happening when they come through the opening?
They expand.
What shape? They're curved, right? They're a curve. This is a property of waves. It's got an ability to bend around an edge. It's not changing medium. It's still in the water, but as this wave is moving through the water, part of it grabs hold and kind of slows down almost, and the other part lags behind. One part pushes through, it kind of bends and it goes around, and that bending is called diffraction. Diffraction. So this is another property we said. Remember, if something is a wave, then it can reflect. Another property of waves is they can diffract, okay, which means that they bend without changing medium. And so then you can see too, if we make this opening a little bit smaller, well, if we make this opening a little bit smaller, what does come through has a larger curve. If we make this opening a little bit bigger, what does come through doesn't have as big of a curve, but it does bend more at the edges, you can see. Kind of cool? If you've ever gone to the beach, you notice that when the waves are out deep in the ocean, they look pretty uniform, okay? But when the waves come crashing into the shore, the depth of the water changes. And so when the depth of the water changes, yep. See if we can show this. As the depth of the water changes, something else changes in the wave itself. So let's try to... I don't know how well you can see this on the... But if you look at either the screen or at the ceiling, but can you see that the edges, the waves that go over the yellow plastic and the waves that are on the edge of it, beside it, they're not lined up. Can you see that? So what happens is the wavelength is getting squunched together as it's going in this shallower water. Okay? So picture this as waves in the ocean. As they get to the shore, the water is shallower, and so what happens to the wavelength? It gets shorter. So what happens to the frequency of the waves as they crash onto the shore? If the wavelength gets shorter, how often does that happen then? More often, more or less? more often, right? So the frequency increases, and that's what happens here. To keep the speed the same, as the wavelength decreases, the frequency increases, and the speed stays the same. And you can see that the waves that are in the deeper water have a bigger wavelength than the waves that are in the shallower water. Kind of cool?
Yeah.
And then one more thing that I want to show you, as far as waves being able to interfere with each other, happens when we can get a couple of point sources together here. So let's change this to steady. I'll change this. And just put these on here.
Mom, increase your amplitude as well.
Do what? Increase?
Well, once you get done with that, Mom, increase your amplitude.
Okay. I can just put these on here, right? I'll snap them.
All for those.
So these are 2 point sources. Like earlier I was, tapping in the water like this, right? These are 2 point sources that are going to tap in the water here. I don't really want that. There we go.
So pretty.
There you go.
Oh, that's cool.
So these 2 points are going tap, 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 tap in the water, and they're creating circular waves, right? Those circular waves are interfering with each other. And actually, I do want this strobe on. You can see areas of bright and dark, right? Okay. Once again, your brightest areas, the bright areas are where the crests, the troughs are. The dark areas are where the crests are. And each wave, even if it was crest to crest and crossing over, or trough to trough and crossing over, you get this amplitude that you. And so, can you see? Let's see. Can you see something that looks kind of like wagon wheel spokes that come out? Can you see the spokes that come out? This pattern is called a moire pattern. And it's an interference pattern from 2 points that are, and you can vary the distance apart with them. But these 2 points have the same frequency, and as the circles that they make, the waves that they make interfere with each other, then you can see where there's constructive interference and destructive interference, and then you see these spokes that radiate out, which is kind of cool, especially on the screen. You can see kind of those, almost look like just gray bands that are coming out, like wagon wheel spokes. Okay. This is still bobbing up and down 20 times per second, but if you're looking at it, it looks like it's going really slow. But it's definitely not. We take this to a steady light.
Hey, finish.
Okay. Kind of cool, huh? If your eyes try to follow it, you kind of get sort of the same pattern effect that you had as you were going when the strobe was doing it for you. But you can see that moire pattern pretty well on the screen. Kinda cool, huh?
Yeah.
Anything else you wanna do, Mr. Capri?
I think that's it. We can line them up if you want.
Oh, yeah, let's do that.